Have you ever stopped to think about how a computer actually predicts the future? I'm not talking about science fiction, but the very next microsecond in a really complex system. Like, say, how heat spreads through a metal bar. Teaching a computer to solve these kinds of problems is honestly at the heart of so much of science and engineering. So let's dive in. We're going to explore two really powerful ways to do this and uncover a hidden trap that's lurking in the simplest approach.
It sounds nuts, right? You've got a perfectly good model of physics, you hit the run button, and instead of a nice, clean simulation, you get total, absolute chaos. This is the big mystery we're unpacking today. Why is it that one tiny choice, one wrong step, can cause an entire simulation to just, well, explode? So, the problem we're trying to solve is all governed by this elegant little rule you see here, the diffusion equation. You can think of it as the universe's instruction manual for how stuff spreads out. We're talking heat in a pan, smoke in the air, you name it. This equation is what describes that smoothing, spreading process. Our whole job is to teach a computer how to follow these instructions, one tiny step at a time. Okay, so where do you even begin? Well, the most natural, most intuitive way is with something called the forward time central space method, or FTCS. We're just going to call it the explicit method. And it's exactly what it sounds like: direct, straightforward, simple. The logic here is it's pure common sense. To figure out what some point is going to be like in the next moment, you just look at what it and its neighbors are like right now. You take all the information you already have from the present, you plug it into a formula, and boom, you calculate the future. It's a one-way street moving from the present to the future. And here's the magic. See how the future value over on the left is calculated entirely from stuff on the right that we already know. It's computationally cheap, it's easy, there's no big complex system to solve. This is what makes it so incredibly fast for each little step forward in time. But this is where our simple hero gets into trouble. That amazing speed and simplicity, it comes at a really high price. There's a hidden danger, a kind of stability trap that can completely destroy our results. Let's see what that actually looks like. So it all comes down to this one critical rule, known as the CFL condition. For our method, it boils down to something really simple. That little d value, which is basically a ratio of our time step to our grid spacing, it has to be less than or equal to 1/2. What that really means is you can't take big, greedy steps in time if your view of space is really detailed. You have to be careful. And when you follow the rule, everything's perfect. You take your small, careful steps into the future, and the simulation gives you this beautiful, smooth curve. It shows the heat spreading out exactly like you'd expect in the real world. It works. But break that rule even by a little tiny bit, and this happens. This is the stability trap in action. The solution doesn't just get a little wrong, it completely blows up. The numbers just go haywire, oscillating bigger and bigger until it's all just meaningless noise. Your simulation has crashed, all because your time step was just a fraction too big. So if our fast and easy method is also super fragile, what's the alternative? Well, that brings us to the implicit solution. We'll call it BTCS, and it offers a much, much safer way forward. You see, the implicit method has a totally different philosophy. It says, hey, wait a minute, the future of any one point actually depends on the future of its neighbors. It gets that you can't just figure out each point on its own. Instead, it builds this big, interconnected system of equations and solves for the future of all the points at the same time. And you can see that difference right here in the formula. Notice how the future values, the ones with the n+1, are all mixed up together. You can't just calculate one directly. You have to solve for them all at once, like a giant puzzle. Now, this takes more work per step, for sure, but that extra work is the key to its power. And here is the huge payoff. This method is unconditionally stable. That means you can take whatever size time step you want, big, small, massive, and it will never, ever explode on you. It might get a little less accurate if your steps are huge, but it will always stay stable and give you an answer that makes physical sense. So this brings us to the ultimate trade-off, really. It's not about one method being good and the other being bad. It's a strategic choice you have to make between speed and safety. And honestly, understanding this trade-off is what really separates a beginner from an expert. Okay, let's put them head to head. When it comes to stability, FTCS is conditional, it's fragile, while BTCS is unconditional. That's a huge win for safety. Now, cost per step, FTCS is cheap and easy. BTCS is more expensive. And the key downside for each? With FTCS, your time step is just stuck. It's limited by that stability rule. With BTCS, if you take really big time steps, your solution can get a little bit fuzzy or artificially diffuse, but it won't crash.
So, with all that in mind, how do you actually choose which one to use? Well, like with so many things, it really just comes down to using the right tool for the job. I like to think of it like this. FTCS, the explicit method, is a sprinter. It is incredibly fast over short distances. It's perfect for quick tests, simple problems, or when you can run millions of tiny little steps all at once on something like a GPU. BTCS, the implicit method, that's your marathon runner. It is built for the long haul. You use this one when you need to simulate something for a long time, or when your grid is super fine, or anytime stability is the absolute #1 most important thing.
So, the question we're left with is really a question for you. When you come up against a problem that changes over time, what kind of solution do you really need? Do you need the raw, blazing, but conditional speed of the sprinter? Or do you need the robust, never-gonna-fail-you safety of the marathoner? The right answer? It all depends on the race you're running.